Thanks for coming. So we have a talk about self-supervised learning, and the presenter is Levan, Tsinadze, head of AI at Maxin.ai. That's probably the largest AI-related company in Croatia. So please,
Thank you very much. Hello, everybody.
louder, I think.
Okay. And today I will talk on maybe this idea how to generate labels for self-supervised learning, or approach for self-supervised learning, especially for specific data sets which we use in practice, and which are not included, are far from the general domains, general domains. Transfer learning, yeah, I would go through the history a little bit. I must have to. Maybe for somebody it might seem a little bit boring, but even now, we have this self-supervised movement, open data sets and open models, to train on huge amount of data like CRIP, which seem to work very well and generalize very interestingly with sufficiently bunch of specific data sets. Even now, the training model on imaging is a de facto backbone for almost all computer vision tasks. I mean backbone. And of course, with limited choice of custom models, because there are many backbones present family, and mostly it is present. Many data sets are domain specific. This is the major thing we can shoot to that. Only have this singular distribution features imaging. Can you speak louder? They don't have the same distribution. See, distribution of features, distribution of colors, distribution of contours, this image data. For instance, medical data, which might have a different amount of channels and color space, satellite images, biological images, etc. So for specific tasks, we have to come up with some idea how to train our model to avoid hand-labeling a entire data set, which is expensive for our experience, which is time-consuming. It tends to be biased and has errors. For instance, ImageNet, which has 1 million data set over the 1 million data items. It's almost impossible to reach that amount of data in a short amount of time, which we have. So it is even more expensive to label data for segmentation, classification, and to label each pixel or each boundary box for each object. We have many different tasks, and then we need good representation for specific domain. For instance, when we have small input images, like for object tracking, mostly it is object tracking, object counting, and sometimes these models goes in embedded devices, video analytics. Our company is outsourcing companies, consulting companies. 90% we are limited with our resources. But they have, or they can report and provide with labeled data. sometimes unlimited amount of data because they have these videos, they have these wireless cameras, they have equipment, and they use this equipment and they record data and then analyze data in machine learning. Deep neural networks has strong representation capacity of various tasks. Self-supervised learning is one of the ways to pre-train models to use them as a backbone for different tasks. The self-supervised learning is the learning technique when labels are generated automatically from input data. Often these labels, it doesn't make any sense in terms of final goal. But sometimes does. Sometimes not directly related to final goal, but sometimes unscrupulous issues in the generation. And of course, there is trade for background model representation part of model. Use this model as additional layers. There has been researches, different techniques for self-supervised learning, especially in the last 10 years. Position louder. Relative positional patches when 8 patches were specific patches or location or number of patch. They call code patch according to patch. There was context encoders communicating images. I think one of my favorites is rotation classifier, which was a pretty simple idea, and I would say made significant step forward in self-supervised learning. When they just take data set, rotate it, and predict rotation from original data, from rotated data. And they have only 4 labels: 90-degree rotation, 170-degree rotation, 180-degree rotation, and 0 rotation. And model that to degree which rotation was used for input data. Pretty simple, yes. And in fact, first glance, some might think that how representation might be learned from simple rotation. But as you see, in some cases, for instance, in the case of dog, features are straightforward and rotation is obvious, but here, model has to pay attention not on the branch, but on the beam in order to predict proper rotation. Because branch might be in the similar position in many images with 0 rotation. The model has to extract more scrupulously, more complicated features from images, from source images. Here, sorry for watermarks, but rotation classifier I believe on significantly larger data set, billions of images. They do nowadays. Both learn and extract more complicated features and might have even more and better features in the same representation or as modern networks trained with modern techniques. But I would say that it might have its honorable place in the world of representation. So if we compare self-supervised learning, model has to cover more details from the input to predict proper rotation. As you see here, for instance, in this case, model has to pay attention on the glass. But if glass is in the proper position, model has to pay attention on the background. So model has to find the parts of images to pay attention on this part and cover maybe complicated features. And I cover more feature space than simple context encoded or relative position information. For fully supervised learning, model has to extract features from one particular object. Model has to learn one particular object. Often one particular object. I include classification tasks, which I would say common pretext tasks here nowadays, mostly on the chat. Objects often are located in the center, especially in the data set. There are augmentations, of course, cutout, blue, random crop, etc. to make double pay attention to different input features, but still the features are probably limited to multiple objects, not all the objects, for instance, or even less objects than the data sets. I would say a huge step forward in self-supervised learning was contrastive learning. I think CPC was first, and most recent works they have nearly the same performance on linear elevation and image differences 0.05%. And even better, performance on various downstream tasks like object detection, semantic segmentation is achieved with contrastive learning and overperformed in genetic trained models. So, representation from the different orientation of the same images. The idea is pretty simple. It came from representations from the different orientations of the same images are attracted in the case of the images and images from the data set and repeat. Louder! The loss function mostly used in well-known techniques. It's info, non-contrastive estimation, and as you see, without negative samples, it might converge to trivial solution. The loss might just converge to zero. Put everything, every vector zero, and loss will be small enough. There will be global or loss landscape. The loss function for contrastive learning needs as many negative examples as possible. As it was presented previously, with some unrelated presentation. So this makes batch size, of course we cannot have entire data set representation as negative samples. Batch, and we limit ourselves on batch. Is my sound enough, or should I speak louder?
More is better.
More the merrier. I hope folks won't hear me really slow. And make it even louder.
Don't worry.
So we need to come up with bigger and bigger batch sizes, which is expensive, which needs more GPU memory, and more GPU memory means more GPUs. We cannot have custom GPUs. We have limited memories in single GPUs, and more GPUs means more memory. There are positive only learning approaches. I would say they are brilliant. Bootstrap your own latent, which was presented here a couple of hours ago by one of the authors. And Barlow twins by Facebook, Barlow twins, self-supervised learning via redundancy reduction. All of them use peer as an input data. Why don't we preserve augmentation information to make our model more sensible, more sensitive for this augmentation information. Equip this information with topological/metric properties and use it as a target for training using peer of input data. For each peer, let's use not one-dimensional distance, but use vector equipped with distance. Vector from metric space. Single augmentation would give us much information, so we should have, in order to get reasonable target, reasonable amount of dimensions, we should have multiplier augmentations. But too many augmentation might overcomplicate our task. So use several augmentation on single item along with mixed augmentation with different items. This was a simple idea. With multiple single and mixed augmentation, for instance, cut mix of two images, crop, rotate, mix up with other images, cut part of image and mix up with grayscale, resize different image, and put a patch in third image. To generate multiply relationships among augmented images. So we have kind of graph, yes, augmentation of these images. And this graph, they don't have single-dimensional nodes, yes. They might have several steps of augmentation of the same images or of the completely different images using mix-up augmentation. Cut part of the one image, put it into the second image, crop the second image, and maybe put it or mix up this third image. So we can involve as many images as we want, and we can have as many steps as we want. More hyperparameters, the more we measure. Again. So we have kind of multidimensional, multi-relation. Each augmentation, if you consider each augmentation as a relation, we have multidimensional relation. Yes. And multidimensional, it means it's somehow projectable in Euclidean space. Yeah. That is what we call multidimensional relations. Let's define so-called projection in Euclidean space, our relations, our different augmentations. For each pair of images or input data in general, define vector, and each coordinate of this vector represents different augmentation. For instance, for cut mix, we can put in appropriate dimension area of cut, which represents amount of one image in another. For random or center crop, we can have this similar picture, but on different dimension. For mix up, put mixed parameter alpha or mu. What do you call it? In appropriate dimension, which might represent difference between original and mixed images. Different is two original and one mixed images. So we have three images involved already. Rotation or blurring or other augmentation might be considered as a single picture on the single images, which might enrich our picture space. Put it in higher dimension. So we project our relation on topological or metric space. Actually, this projection, this might be chosen smartly, like handcrafted smart projection. And it depends on final task. In this case, our augmentation, our pretest task is, I would say, hardly bounded in final task. For the future, we think we can come up with asymmetric space, asymmetric relations, directed graph. We have multidimensional, which includes multi-step mixed augmentations, multi-images. They don't have a single or two images involved. Rotation for single image, mix up for image G, EI, and cut mix for image G, etc. For plus or here, we can manipulate these different augmentations and get a class of different projections, which we hope will avoid the model's trivial solution or degeneration. So we define representation model, which might be relatively fashionable, but it might also be some custom model which is used by us for object tracking to generate representation from already detected object, already extracted object. In many cases, we have custom small models, customization of various small models. And we just define CMS network in this case. Along with projection head, and this projection head might be just concatenation and then projection in the same dimension as our augmentation projections. Or it might be just some or more invariant cases that will use projection. I just suggest that it might be interesting. Oh, this was my experiment with LaTeX presentations. And try to fit the model to make this diagram complete. So we have Siamese network here. We have relation of images, projection of this multidimensional relation in Euclidean space, and we have this projection head from representational space,
So, I'm sorry, so this RDE on the bottom right,
yes.
That's basically a vector which represents augmentation style or whatever, right? How is it augmented?
It represents many different augmentations.
Yeah, at once.
Yeah, in one vector. Each augmentation might be encoded in one or several dimensions.
And now you want to predict that one
Yes.
from your representation.
Yeah.
So in the example of rotation, that would be a vector which says the vector at the bottom would be
the vector which has in appropriate dimension has instance or one potted four-dimensional.
Okay.
Part of it will be rotation, but there are several steps of augmentations, and there are mix-up augmentation from different images which make this relation less sparse, I would say. We don't have only pairs of relations. So. And we can manipulate in order to regularize our model from trivial solution and from degeneration to overfit, from the augmentation of parts and augmentation of features. Okay. Actually, it's an idea which worked in practical cases for us. I think this idea had potential to be developed and used as academic research. But who knows? It will be, I hope it will be done at the end of the year, not this year, at the end of these 2 semesters, by the spring. So, we did not measure our performance on benchmark datasets. I'm sorry, that's why I was talking about academic performance. We did some experiments on relatively small datasets like MNIST, FashionNIST, CPAT, STL, but maybe significant result, but not confident about them, sorry. But small datasets, because all our practical tasks need features on very small patches of images. And we have several ideas which might be developed interestingly. For instance, maybe cover entire projection space R with small radius balls, and which might consider as a clusterization in order to reduce overfitting to particular augmentation with less augmentation, less dimensional projection, less augmentations, I would say, and train model in particular cluster. That might be a mix of clusterization and then train. Augmentation is clusterization. This gives us more information about nearby elements, which might include several steps. But for nearby elements, I have I will show you. And this will encode information, more information, gather and accumulate more information each vector. We kind of try this, but didn't put enough effort, I would say, But the major idea which we are working right now is graph neural network. So we have, we can just consider our relation of augmentations as a graph, yes, as a directed graph, or indirected. It depends how invariant our model should be. So we have for each peer, but it's not a regular graph. It's not just direct projection of graph, like direct mapping to graph. We have graph for peer, and we don't have graph Cartesian product, direct random Cartesian product. We just use node. We just consider node among graphs if we have composition of relations. So we have if we can consider we can call node if we have relations of two elements, like UP is related to UQ, whereas UQ is related to UK. So we have some vector in the middle, I would say. And so this might be considered as a match. This was done, we tried, we are thinking we should avoid only edge features. We somehow need node features, and node features we have already well-known and well-working self-supervised networks on graphs, which accumulate nearby information from neighboring edges, neighboring nodes. But the edge feature, we weren't able to find sufficient, I would say, paper with code with sufficient results. So this manipulation is done in order to avoid edge features and use only node features. And then use graph neural network. Graph neural network has this amazing ability to accumulate, aggregate neighboring node information with self-supervised learning. This well-known self-supervised learning algorithm from aspects of the graph, then self-supervised networks simply use multiple graphs, sometimes better than because they have structure. So we believe that different self-supervised learning algorithms on graphs, like graph for node representation, we accumulate node information. More neighboring and neighboring information, several step information depends on the amount of layers for each peer of our data. So these pretext tasks might be more robust for generalization. This is just our hypothesis which we are working for. We have two approaches. One is dynamic generation and training, but our experimenting is better to create as many augmentation with relations as possible, save them on the disk, and experiment with different other parameters. The same for graph. Graph might be generated before training with augmentation. Graph might be pre-trained before training, or even extract features from each input data and train and add these features, combine these features with node features of graphs. I don't think this applies because convolutional layers plus graph, convolutional layers might be computationally immensely expensive, especially for organization like us, a company like us, would not afford that much resources for these experiments. Thank you very much, and if you have questions,
Let's have one question now, and then we can go to the other, continue with the other talks, and Levan's here, so you can ask questions anywhere, any time of day, maybe after party, or during the other talks.
Or reach us on Data Science BDC or Data Science everyone, and most groups, I follow most groups, and if you come up with an interesting idea or hypothesis, I'm glad to cooperate.
Do we have a short question? Okay, let's move to the next talk. So thank you again.